Sure. Next speaker, Nina Balcan from Tech, talking about active statistical query.
Okay, well, thanks, Avrim. So this is joint work with Vitaly Feldman, who is sitting somewhere here. Yeah. And just to put this into context, let me start with a 2-minute version of this talk. Okay, so at the high level, this talk is about learning algorithms that are active and try to minimize the need for expert intervention. Okay, so as you might know, the classic supervised learning approach depends on the assumption that humans can annotate or label all the data available for training. Okay? However, most modern machine learning applications have massive amounts of raw or unlabeled or unannotated data. Okay? And this is why there has been tremendous effort and interest in recent years in machine learning to design learning algorithms, in particular active learning algorithms, that most effectively utilize all the available data while minimizing, again, the need for expert intervention. And this has been a major area of research in machine learning and learning theory, with many exciting results concerning the label complexity, the sample complexity of active learning. Okay? However, very much less is known and very few positive algorithmic results. Polynomial time algorithms have been proposed that can tolerate noise. And in this work, our original goal was to address this problem. And in particular, what we do in this work, we propose a framework for designing a certain type of learning algorithms called statistical active learning algorithms that, oops, oh no, postpone.
Just talk fast, you got it.
Good. Talk fast, yeah. I'm sure I can talk very fast. That's not a problem. Right. So in this work, we design a framework. We present a framework for designing a certain type of algorithms, namely statistical active learning algorithms that enjoy 2 main properties. So first of all, in this framework, we can transform any polynomial time statistical active learning algorithm that is probably effective in noise-free scenarios into polynomial time active learning algorithm that is probably effective when the data is corrupted by random classification noise. Okay, and we also, for commonly used concept spaces like thresholds and linear separators, we also present statistical active learning algorithms. So these 2 facts together lead to the first known algorithms, active learning algorithms that are label efficient, polynomial time, and can tolerate random classification noise. Okay? And second, and this is very relevant for this workshop, we show that the algorithms that we design in this framework very naturally satisfy differential privacy. Okay? And this could be highly relevant for scenarios like financial record analysis or medical record analysis, where the data is both expensive to label and sensitive. Okay? So this is a 2-minute version of my talk. Now, in terms of the structure of my talk, I will first start by briefly reminding you the typical way to analyze learning algorithms in the passive supervised learning setting. Then I'll present the statistical query learning framework for passive learning. Then I'll introduce active learning, the way it's normally described. And then I'll present our model and describe the results in this model. Okay? So in the classic supervised learning setting, which is captured by the classic models of the path model of Elliott and the statistical learning theory framework of Warnick. So in this model, the learning algorithm uses labeled examples. So for instance, email messages labeled as spam or not, if you want to do spam detection. Okay, and formally in these frameworks, we assume that there is some underlying probability distribution over the space of unlabeled examples. And for instance, over the space of email messages. And in the training phase, first, the learning algorithm gets to see a random sample of these examples. These examples are then labeled by an expert, and these labeled examples are then input to a learning algorithm, which then outputs a classifier, right? And the goal of the algorithm is to output a classifier, but that's all on random examples that come from the same underlying distribution. Okay, so formally in the settings, the learning algorithm gets to see a set of labeled examples which are assumed to be drawn IID from some fixed but unknown distribution over the instance space, and they are labeled according to some fixed but unknown target function C star. Okay, and for my talk, I'm actually going to denote by P the distribution induced by D and the target function C star. Right, and in the PARC model, we also assume that the target function itself comes from a known concept class like linear separators, but it can be anything else, decision lists, decision trees, and so on. Okay, and when the goal of the algorithm is to do some optimization over the given sample in order to find the hypothesis that has a small error rate with respect to the original distribution. And for my talk, by error rate, I really mean the classic 0-1 error loss or classification error loss. And basically, probably most of the algorithms that we have seen, like AdaBoost and SVM, have been designed for this scenario. Okay. Now, so this is the classic way to analyze passive supervised learning algorithms. Now, motivated by the idea of trying to have a unified way to design learning algorithms that are tolerant to random classification noise, Michael Kearns introduced in 1993 a framework called the Statistical Query Framework for Passive Supervised Learning. Okay, and so this is a framework for designing learning algorithms that only operate via statistical properties of the data rather via individual examples. Okay, and in particular, the way to think about these types of algorithms is that they interact with a statistical query oracle in the following way. So what the algorithm can do, he can ask, please tell me what is the probability that a random examples has some property phi. And please tell me that up to additive error tau. Okay, so basically the SQ algorithm interacts with the SQ oracle by a number of such queries. And based on such queries, he updates his own hypothesis. And then at the end, the goal of the algorithm is to output a classifier of true error rate at most epsilon. Okay, just as a quick example, assume that we are trying to learn a threshold function on the real line. Actually, even let's assume that we are trying to learn a threshold function in the interval 0, 1. And just for instance, in the special case, when the underlying distribution is uniform, we know that it's uniform, then what we can do is just simply ask the SQ oracle, the query, please tell me what is the probability that a random example is positive, and please tell me that up to tolerance epsilon. Okay, and once you get this back, it's very easy to see that we can output 1 minus p, and the hypothesis that will output will have true error rate at most epsilon. Okay. Now, when the underlying distribution is not uniform, so in general, after we get the answer to the first query, what we have to do is to then ask a number of unlabeled statistical queries and to find the point z such that the probability that a random example belongs to the interval 0, 1 is very close to p, and then we can again output z. And it's very easy to see that actually this will have true error rate at most epsilon. Okay? So this is just an example. Now, in general, these statistical query algorithms enjoy a number of interesting properties. Okay, and the first one is that we can simulate statistical query algorithms from random examples. And this is simply just because we can estimate the result of a query phi up to tolerance tau just from the empirical with very high probability from the empirical by using the empirical expectation over a 1 over tau square log 1 over delta random examples. Okay, so basically, if we are able to design a learning algorithm that uses only a polynomial number of statistical queries, such that the tolerance tau is not too small, then we immediately also get a polynomial time algorithm for the usual PARC or statistical learning theory framework, where the algorithm has access to random examples. Okay. Now, to be totally honest, I don't particularly think about learning algorithms in the SQ model, so they might look a little bit non-intuitive at first. But the nice fact is they enjoy two main properties, and in particular, the first one is that they can be easily made robust to random classification noise. So in particular, that we can basically, so if we have a polynomial time algorithm that is statistical and is computationally efficient in noise-free scenarios, we can immediately transform it into a polynomial time algorithm that is tolerant to random classification noise, where the label of each example is flipped independently with a fixed constant probability. So they have strong noise tolerance properties. It's a generic reduction. Okay, so that's a nice thing. And in fact, many known machine learning algorithms like perceptron and so on do have statistical query analogs. Having presented the first one in '96. In fact, almost everything that we know to learn efficiently can be learned via statistical queries, via statistical query algorithms. So they are pretty general. Okay, and from the point of view of this workshop, the very nice thing is that algorithms designed in this framework can be very naturally turned into algorithms that satisfy differential privacy, which can be relevant for many scenarios. And this fact is from a 2000 paper by Blum, Dwork, McSherry, and Nissim. Right? So the statistical queries algorithms have a number of very nice properties. Now, this is all about passive supervised learning, and which I mentioned earlier. It's a technique, it's an approach, learning approach, that operates under the assumption that humans can annotate all the data available for training, right? Which is clearly highly unrealistic for many of the today's settings. And as mentioned, the technique that has been developed, or an approach that has been considered for circumventing this is active learning, which is what I'm going to talk about next. Now, so what is active learning? Let me take a I didn't expect it, but it looks like I also have an active learning expert in the audience. So, right, so what is active learning? So actually the easiest way to describe active learning is here's Lei Wang from, yeah. So, right, good. So the easiest way to describe active learning is in the normal learning scenario where you have access to random examples, okay? So in the active learning scenario, the learning algorithm first gets to see a large set of unlabeled examples, and then it can interactively ask for labels of unlabeled examples of its own choice from the pool. Okay, and the goal is to use this interaction in order to drastically reduce the labeling effort. Okay, so basically in this scenario, we assume that the learning algorithm has access to large amounts of unlabeled data, and and also it can interactively ask for labels of examples of its own choice. And so the goal of the learner is to be smart, to be adaptive, in order to learn with much fewer labeled examples. So really, the algorithm wants to pick examples that are somehow informative in order to be labeled. Okay, and let me just mention that from a theoretical point of view, the canonical example showing that active learning can be actually significantly better than passive learning is again that of learning a threshold function. In this case, it turns out that active learning provides an exponential improvement in label complexity over the classic passive learning. And the argument is really simple, so I'm just going to quickly go through it. So let's just assume noise-free scenarios. Then what we can do, we first can just draw 1/epsilon unlabeled samples. Now, if we knew the correct labels of those unlabeled samples, just from standard sample complexity results from passive learning, we could just output a consistent classifier to those labeled examples, and we would know that with very high probability we are doing well. Now, the key point is that in active learning, we can just do binary search. And with only log 1/epsilon requests, we can infer the true labels of those 1/epsilon unlabeled samples, and then we can output a classifier that is consistent with those, which with high probability will be very accurate. Okay, so basically in active learning, we only need log 1/epsilon label requests to learn an epsilon accurate classifier. Now, passive learning probably requires omega of 1/epsilon label requests, so you get an exponential improvement in this simple case. Okay. Now, this is just a simple example. Now, the question of when active learning provides an exponential improvement over, or when active learning actually provides significant benefits over passive learning has been studied in the recent years in much, much more general scenarios. And there has been a lot of exciting activity in this area. Now, for the purpose of this talk, I'm going to roughly classify the results into two categories, just to put my work into context. So at one extreme, we have very, very general active learning algorithms called disagreement-based active learning algorithms, which at a high level operate by keeping a set of surviving classifiers. So by going round, in each round they have a set of surviving classifiers, and in that round we only query points if they fall in the region of disagreement of the current set of surviving classifiers. So if they are in the region of agreement, we don't have to query for the label, so we only query for labels of points that fall in the region of disagreement. Okay, and we use those labels to then throw out classifiers from consideration if we are statistically confident that they are suboptimal. Okay, so this is how these algorithms operate at a high level. Actually, the first algorithm of this type was analyzed in one of my old papers. And then it has been reanalyzed and in even more general scenarios, and variants of these algorithms have been proposed by many researchers. So this is a long line of work, and including Lei Wang here, he has analyzed this type of algorithms. Now, these algorithms have a very nice property that they are very general. They work for basically for any type of noise, even adversarial label noise. Okay, so this is their main benefit. However, the main problem is that they are computationally inefficient. Okay, so that's the main problem. Now, this is one extreme, and this is really where most of the work in active learning has been spent in the past 10 years. Now, at the other extreme, we also have very specific results that are computationally efficient, but for very specific constant spaces like linear separators, and really only when in the noise-free scenarios. Okay, so for instance, many researchers have shown in various ways that, for instance, if you are trying to learn a linear separator in RD, so in high dimensions, then if the underlying distribution is uniform over the surface of the unisphere, you're going to get an exponential improvement in sample complexity. Okay? So really, the two types of results that we have currently in the literature is at one extreme, we have very, very general computationally inefficient algorithms that work for adversarial type of noise. At the other extreme, we have very specific algorithms that only work for very specific cases, but only for noise-free scenarios. So really,
the exponential improvement in D or epsilon?
Epsilon, the accuracy parameter. So it's like
D is still required, right?
You go from D over epsilon to D log 1 over epsilon, and that's probably the best you can do. There is a lower bound, actually, in one of my papers. Yeah? Yeah, please ask questions, of course. Good. Right, so basically, so in this context, really the main open question in this area is to design polynomial time algorithms that are label efficient. So we want to design polynomial time active learning algorithms that are label efficient, but also tolerate noise. Okay, and this was the original motivation for our work, and this is why we introduced this active statistical query learning framework, which is a framework, as I mentioned earlier, for designing polynomial time active learning algorithms that are tolerant to random classification noise. And as a bonus, they also enjoy very nice differential privacy guarantees. All right, so now in our framework, instead of having access to random examples, our algorithms will only get active estimates of statistical properties of the data in the following sense. So now a query, it will be a pair. So it's a filter function chi and also a property phi. Okay, and the filter function chi specifies the probability that we're going to query the label of example x. Just for simplicity, you can think of chi as just being the indicator function of a set of informative examples, and of property phi as some property of the target function that you want to estimate. Okay, and so then basically from the algorithm, our learning algorithm can get from the active SQ oracle an estimate of the probability that property phi is satisfied on a random example, given that that random example also satisfies the filter chi. And it gets this estimate up to additive tolerance tau if the probability that the filter chi is satisfied is lower bounded by this filter tolerance tau f. Okay, and then the learning algorithm can interact with the active SQ oracle via a number of such queries, and the goal is to output a classifier of small error. Okay, and now the key point is that when we simulate this from random examples, the number of labeled examples only depends inversely polynomially in tau. So it only depends on 1 over tau. And the smaller filter tolerance will actually going to go only on the number of unlabeled examples. So that's the key point. So basically, it's easy to see that we actually can simulate such a query by using so many labeled examples, so many unlabeled examples, right? And the interesting fact is that now, if we can design an active SQ algorithm where we are able to keep the tolerance tau large, even if the filter tolerance potentially becomes small, we get significant benefit in the number of labeled examples that we need to learn well.
Can you explain filter tolerance again?
So I'm going to have an example. So okay, I can go back and explain it, but I also have a quick
Your
example.
example will make it clear, that's fine.
I think the example will make it clear. If it's not clear, it's, then I'll come back. Yeah? So let me know. Good. So let me just make a couple of comments. Actually, maybe I can just jump direct to the example and come back to the comments later. Okay, how about I do that? Okay, so just to, good. So let's go back to the threshold examples, right? As I mentioned earlier, in the passive SQ, in order to learn well, all we have to do is to ask the query, please tell me, so if the underlying distribution is uniform, in the passive SQ, all we have to do is to ask the query, please tell me the probability that a random example is positive, and please tell me that up to tolerance epsilon. Once we had that back, we had an accurate classifier, epsilon accurate classifier. However, in order to answer this query, we needed 1 over epsilon squared labeled examples. Now, the point is that when we do active learning, we can use the filter and we can localize. And we are able to design learning algorithms that only use constant tolerance. So constant tolerance tau, even if the filter tolerance tau f becomes smaller, we only have constant tolerance tau, so we're going to need fewer labeled examples. Okay, and just to make this more concrete, let's assume that we currently know that our threshold function belongs to the interval AB. Yeah? Now what we're going to do, we can ask the active statistical query, which is, please tell me the probability that a random example is positive, given that it falls in the interval AB. And we're going to ask, the filter tolerance, we're going to put the filter tolerance here to be epsilon. So we're going to ask this question only if the interval AB is not too small. Right? This is where the filter tolerance comes into place. Right? We're going to ask this question, please tell me the probability that a random example is positive, given that it falls in the interval AB, with the intolerance tau, which is 1 over 4. Okay? Now it's not, one can just go for a little bit of math, and it's not easy, it's not difficult to see that we can use the answer to that query with intolerance 1 over 4 to then basically output an interval A prime B prime that is twice smaller than the interval AB, which is a property that the target function belongs to that interval. Okay, so in this case, basically the filter tolerance itself can go very small. It can go up. It will never be smaller than epsilon, because on the interval A prime B prime is smaller than epsilon, it's stop. But it can go as small as epsilon. However, the tolerance itself that we use is only constant. So basically, we'll go for log 1 over epsilon rounds. In each round, the tolerance tau we need is 1 over 4. So basically, we need a constant number, pretty much a constant number of labeled examples to answer such a query, potentially more unlabeled examples, because the filter tolerance can be as small as epsilon right before the last round. But the key point is that we go log 1 over epsilon rounds. In each round, we only need a constant number of labeled examples. So in total, we need basically log 1 over epsilon labeled examples. And more unlabeled examples, 1 over epsilon unlabeled examples. So did I clarify?
So your chi is adaptive. It changes from round to round.
Absolutely, yeah. That's
it's not clear from the first definition.
Yeah.
It's one chi, but it's not one.
It's adaptive. Even chi, even if 5 will be, I can allow them to be adaptive. Definitely. Okay, let me just actually go back and just make one more comment just about, so clearly, let me make these 2 notes. Like, I wanted to make 2 notes. So basically, clearly, this model generalizes the statistical query framework of Kearns. A passive SQ is just like an active SQ, where chi is all identity 1, right? Everything is relevant, and the filter tolerance is 1. Okay, and let me also make another comment. So again, the active SQ queries that we are looking at are, please tell me what is the probability that a random example satisfies property phi, given that it satisfies the filter chi. Now, clearly, we can write this as a ratio of 2 expectations with respect to the original distribution. And so, in principle, we could just get the answer to this to our question by using two passive statistical queries. However, to really get this within tolerance tau, we might end up having to estimate this numerator within tolerance tau times this expectation over here, the probability that the random example satisfies times the expectation over here. And so this could mean that we might need too many more labeled examples. So if we simulate it in the usual SQ model, we just need too many labeled examples. So we really want to simulate it in our way, to use the power of being active.
So you're also kind of assuming that it's easy to sample from the distribution chi. And that's, I mean, at least say in the web pages example, that doesn't seem immediately clear.
So well, you can easily, like, you can always kind of write. I mean, the way you can implement this, imagine that you have a large stream of unlabeled examples. This is the way to think about it. You can always implement, imagine that you have a large stream of unlabeled examples, and you're going to go process them you're going to go through these unlabeled examples, and you'll have a current chi. If you satisfy the filter, you're going to use those two for your active estimates. So you can kind of simulate them even if you have like a large set of unlabeled examples at first. IID from the underlying distribution, you can just simulate them.
Assume that these functions are easy to compute once you have CSI.
Yeah, they are for all our examples. Yeah, they're also easy to compute. Yeah, obviously. Okay, so this is just an example. In our work, we have the threshold example, obviously, but in our work, we have a number of interesting results for more interesting constant spices. Now, let me mention just let me mention this noise tolerance property. So, just as for passive SQ, these algorithms can be easily adapted to tolerate random classification noise, and in particular, it turns out that you can estimate these active SQ queries even if the examples are corrupted from random classification noise. Okay, and I'm not going to go through the details. Let me just mention at a high level the idea of the proof. What we do, we're going to break our query into two parts. One of them will be unaffected by noise, this part over here, and one of them will be affected by noise. We're going to estimate each of them within tolerance tau over 2. Now, the part of unaffected by noise, obviously, you can estimate it from noisy examples too. Now, the part that is affected by noise, so for this part, we use the property, our noise model. We use the random classification noise model, and we can get this nice quality over here. And so then basically, if we want to estimate this within, so this is a part we want to estimate within tau over 2, it's sufficient to estimate these parts from noisy examples within 1 minus 2 times eta times tau over 2, or eta is the noise. Okay, so this is basically the high-level idea of the proof of why we can tolerate random classification noise, and it's really very similar to what happens in the passive learning too. Okay, and let me now, I'm not going to have too much time to go through this, but let me mention at a high level. So our most general result here is for learning, I think the most interesting result, learning result, is an active SQ algorithm for learning linear separators in RD when the underlying distribution is isotropic Log-Concave. Okay, and this algorithm, again, we're going to provide an exponential improvement in label complexity over passive learning. And let me just mention at the high level the type of algorithm that we use. It's an iterative learning algorithm. In each round, they have a current guess of the target function, and as we go along, we make it closer and closer to the target function. And in round case, so what we do, we run a passive learning algorithm on a mixture distribution, on a distribution that is a mixture of distributions that are, so each component in that mixture will be the original distribution conditioned on being within a certain band of the previous guess. Okay, and what we do, we run a passive SQ algorithm on such a mixed distribution to get a separator of a really constant error rate, and then we proceed to the next round. And the key point is that we can implement this passive SQ over this mixture distribution by really using active SQs, active statistical queries with a filter tolerance that is never smaller than epsilon. And okay, again, I don't have time to go through the details, but at a high level, it turns out that if you basically pick the margins parameters appropriately, and if you localize aggressively and effectively, then you can argue that only after log number epsilon rounds you make the desired progress. Okay, and moreover, in each round, you can show that you don't need too many labeled examples to make the desired progress. Okay, and I actually have very nice pictures for this proof. If you're interested, please talk to me about it after the talk. It's very nice. I'm going to skip all this. Okay, and I guess go to the main connection to this workshop. So, a very nice bonus of this framework is that all the algorithms that we designed can be made differentially private. Okay, and just to be, and again, this is very relevant for scenarios like medical record analysis, where the data is expensive to label and also sensitive. Okay, and the specific model that we have here is as follows. So we assume that the learner first has full access to the unlabeled portion of some database. Okay, and then the learner can request the labels of some of the elements of its own choice from the database for its own internal use. Okay, and then as usual, the goal of the learner is to output a classifier of small error, but we also want to ensure differential privacy. And for me, alpha is a privacy parameter because epsilon is for the error rate. Okay, and basically what we can show is that any active statistical query algorithm can be made to preserve differential privacy. And now the number of, and the point is that the number of labeled examples will only going to depend on the tolerance tau parameter and the privacy parameter. And only the number of unlabeled examples are going to depend on the filter tolerance tau f, which is typically much smaller, okay, than the tolerance tau. And basically, so and the proof is really standard. This goes in the exact by using the Laplace mechanism in the exact same way as you are in CPI and Kobe did in the earlier work. Yes.
Does it depend on the dimensionality of the space?
Right, well, here I'm using, okay, so the way I'm writing the theorem, I'm saying if you have an active SQ algorithm that uses M queries, M statistical queries, then you can make it differentially private by using so many label requests and so many unlabeled requests. Now, depending on the problem, like for instance, if you are learning linear separators in RD, then the number of statistical queries will going to depend on the dimensionality. Yeah? And so, and basically, so okay, just a couple of nice properties about this theorem is that, for instance, when alpha, which is our privacy parameter, is greater than tau, then we essentially get privacy for free in terms of the number of labeled examples we need in order to learn well. Okay, and moreover, for classes for which we have, for which we provided active statistical algorithms, we like, so for instance, for linear separator or thresholds, basically it turns out that we can learn and also preserve differential privacy by using much fewer label requests than even non-private passive algorithms, than even non-private passive learning algorithms. And this is true as long as the privacy parameter alpha is greater than or equal to the final desired accuracy, epsilon. Which I think is quite nice. All right, and again, I'm not going to go for the proof. The proof is really follows the same lines as the original proof for the SQ model of Arim and Cynthia and Kobe. Okay, and let me just summarize. So basically, in this work, we present a framework for designing. Yeah, questions?
Yeah, so I'm confused
Yeah?
but the relationship between this positive result in lower bounds on sample complexity that we have that also depend on the bit-like representation of the data.
Yeah, so but we're going to the number of unlabeled examples, right? So the way I write this theorem is like if your algorithm needs m statistical queries of tolerance tau and filter tolerance tau f, then you get alpha differential privacy with so many label requests and so many unlabeled requests. Now it could easily be that the bit complexity, right? I mean, so the number of such queries you need, typically the number of unlabeled queries that you need will depend on the bit complexity. Right, if you go back even in the very simple threshold example that I had in the earlier slides, right, I said if the distribution is uniform, then you only need one statistical query, say in the passive learning. right? But however, if the distribution is not uniform, you kind of had to use a number of unlabeled SQs. Actually, let me go back to this slide because I think this will clarify the canon for everyone else. So this is the example, right? Okay, now here. Right, so this example over here, right? So if the underlying distribution is uniform, then you just need one SQ. In the usual model, you need one statistical query, right? However, if the underlying distribution is not uniform, after you get the answer to the first query, which is please tell me the probability that an example is positive, then you then need to do a number of unlabeled statistical queries to find the point z such that the probability that the random point belongs to the interval 0, 1 is very close to p. Now, how many unlabeled statistical queries do you need? It's going to depend on the bit complexity. It will be basically order of b, where b is, is the number of bits you need to write down to represent your examples.
And in fact, we had these lower bounds which show that it has to be the case for differential privacy.
Right, but for instance, going back to this example over here again, so this is for passive SQ. Now, even in the active SQ, so the point is that this bit complexity will go in the number of unlabeled examples. Yeah. So rather than the number of labeled examples. So in a word, what is expensive is the labels, like in many medical applications. What is expensive is to maybe a test. Maybe the test is invasive to see if you have a certain disease or not. This is what is the expensive part. You now already have your features. I want to learn a classifier to be able to say if you have a certain disease or not. What is expensive is for me to run the test on you because it's maybe invasive, right? So because I already have your features, your history and so on, the unlabeled part is cheap, right? So what I want to minimize is the number of label requests. And so in that world, I think these are very strong positive results. And it's kind of cool that this bit complexity often, it's not a theorem, it's just in these examples that I looked at, this is what that happens, right? For instance, this threshold example, the bit complexity goes into the number of unlabeled examples. It could be that for certain problems, the bit complexity also goes in the number of labeled examples, right? But in these examples, it's cool that lower bound is circumventing in terms of the number of labeled examples.
Actually, I have a question. So, in our sample complexity for differential privacy learning paper, what we showed is that if you have a prior on where the unlabeled data is, you can, and let's say your true unlabeled data distribution is a little bit different from the prior, then you could potentially learn with differential privacy, and what you would have to pay is logarithmic in the gap in some distance between the prior distribution and what your true unlabeled distribution is. So would that translate to, could you get these kinds of results for statistical query learning?
So say it again, you have a prior on...
So let's say you have a prior on your unlabeled data.
Okay.
But your unlabeled data distribution is not exactly the prior, but it's close to the prior.
Okay.
And what you could do is you could get like sample complexity upper bounds, which depend on the gap between the prior and your unlabeled data distribution.
Okay, I would expect that you should be able to, yeah.
But the algorithm, was just a bound. So my question is that, can you get these kinds of bounds for statistical query algorithms also?
So again, the word is the examples that you get somehow are not from the true underlying distribution, but from a related distribution.
Yes, from a related distribution.
Your goal is to do well on that related distribution?
No, your goal is to do well on your distribution, but you have the related distribution as a reference to start with.
So how do you use it? Why is it good for you to have it?
Because what we do is we construct, essentially what we do is we look at the unlabeled distribution, and then we construct finer and finer covers of that unlabeled distribution.
So, okay, what is your improvement over the typical algorithms that don't have this prior?
Oh, because you can't, you can't learn in a distribution-free way when you have continuous data.
I see, so just because, I see, that helps you to construct the cover and so on.
Yeah, so you get finer and finer covers. At some fineness, it's also a cover for your distribution, and then you can learn.
Maybe just to illustrate it on this example, if I understand what Tremollik is saying. The point is, in this binary search, if your unlabeled data is, let's say, reasonably uniformly distributed, then you don't need high precision to find a z that gives you this type of kind of z. You don't need to, So there's something. Right. In some sense, if everything were in one dimension, this prior distribution tells you how to rearrange the data so it's close to uniform, and that makes life easier. Right? So that's.
So most likely, I guess the result would translate, but when there's also a question about computational efficiency, that has to be, I guess, that has to be checked. really case by case, I would expect. Because in the end, I mean, we have this framework, but in the end, the computational efficiency comes. I mean, you have to sit down for your specific concept class and analyze if you have a computational efficient algorithm or not. You don't have a magic generic way to design computational efficient algorithms, even, I mean, just statistical algorithms.
Yeah, so I was curious about how this interacts with statistical query algorithms. Is there but we can talk offline.
So statistical queries are a special case of this model, right? So in the statistical query, you don't have the filter. So in the statistical query, you just ask, please tell me what's the probability that the random example satisfies the property phi, and I cannot, I mean, I don't have the filter function, basically. I cannot focus. Let me actually go back again to this slide, because maybe it was too quick, I spoke too fast, potentially. Right, so this is, I think, the main difference, right? So this generalizes the SQ model, right? Because typically, I mean, if this corresponds in the SQ model, the filter function, everything is relevant, right? This will correspond. The filter chi is everything is relevant, right? Now we can, if we have this, right? If we have this filter chi, now the point is that we can focus, right? And we can use fewer labeled examples, even if we need potentially more. I mean, a large set of unlabeled examples. And then again, I mentioned this earlier, but I mentioned it again. So of course. So we can. So this is a type of active. This is an active SQ query. Please tell me the probability that the random example satisfies property phi, given that it satisfies the filter chi. And now, of course, we can simulate this in the passive SQ as well, but we need a lot more labeled examples. So really, the savings comes from the fact that we can filter. We can use unlabeled examples to filter, and only ask for labels in the relevant portion. We can only ask for labels of informative examples, really, with respect to the filter chi.
Just a small type, I think it has to be a filter in the denominator.
Sure.
Yeah. Filter,
yeah, of course. Well, I guess, any more questions? So maybe let me conclude a little bit. Good. So, right. So we present this framework for designing statistical active learning algorithms, and again, the two main benefits are noise tolerance, and also the fact that they enjoy strong differential private guarantees. And actually, just as a comment, maybe at first, actually, when you think about active learning and differential privacy, it's not clear that they are compatible, right? Because in active learning, I mean, the original definition of active learning, you look at specific examples, right? And so in differential privacy, you never want to do that, right? But I guess what we show is in this framework, if you design statistical algorithms, then the two can become compatible. Okay, so then I think it's nice. Now, also in terms of open questions, actually, I think it would be very interesting to basically, so in this work, currently we only look at random classification noise, where the label of its example is split independently of a fixed constant probability, right? So it'd be nice to design statistical algorithms that are also differentially private, but work in the presence of more adversarial noise, like adversarial label noise, even malicious noise, or you can even corrupt the features. So I think that would be interesting. Actually, I have some very exciting recent results with, where we are able to basically design noise-tolerant algorithms. So again, based on the idea of localization, we design noise-tolerant algorithms for adversarial label noise and malicious noise. Turns out that we even improve over the noise tolerance of best-known passive algorithms. So this localization idea seems to be very powerful as an algorithmic technique. Now, I don't know yet if these algorithms are differentially private. So it would be nice to also make them differentially private. And of course, it's always nice to see practical implications of these learning algorithms. Some more questions, I guess? Good. So I guess everyone is ready for lunch.